Hello students, it's Dr. Sands. I'm here to do the Prelab lecture for Experiment 7, which is about Equilibrium and Le Chatelier's principle. Our learning objectives for today have to do with the equilibrium constant, explaining why it's a constant at a given temperature, and also describing the ways that it changes at different temperatures, depending on the thermodynamic quantities associated with the reaction you're studying. Also, we'll be calculating thermodynamic quantities like delta H and delta S and delta G based on equilibrium data from different temperatures, and predicting changes to a mixture using Le Chatelier's principle. In today's lab, we want you to focus on critical thinking skills. And the reason is you're going to be taking a variety of different types of information and putting them together, synthesizing them, to make claims about what you think would happen in a particular situation. I know you're aware of equilibrium from Chemistry 106, but we'll just do a quick review. At equilibrium, the concentrations of reactants and products are constant and no longer change. So if you're looking at a system at equilibrium, it's not very exciting. It looks like it's doing nothing. However, if we could zoom in to the molecular level, we would see that the forward and reverse reactions are continuing to occur dynamically. But because the forward reaction happens at the same rate as the reverse reaction, there's no net change. This is what we call equilibrium. One way that we express equilibrium is using the equilibrium constant. This communicates the extent of the reaction, or the ratio of products to reactants. If the value of KEQ is less than 1, then it means that the reactants are thermodynamically favored. If it's greater than 1, it means the products are favored. And if it's somewhere in the middle between about 1/1000th and 1000, that means that there will be substantial amounts of both products and reactants at equilibrium. When we write our equilibrium expression, we put products on the top, we raise them to the power of their stoichiometric coefficients. We put reactants on the bottom and raise them to the power of the stoichiometric coefficients. And we include gases and aqueous solutions. We do not include solids and liquids. And related to equilibrium, we have this principle that is called Le Chatelier's principle. And it says that when a stress is applied to a system at equilibrium, the reaction proceeds in the direction that counteracts the stress and reestablishes equilibrium. If you remember learning about the reaction quotient, Q, and how you would compare Q to K, Le Chatelier's principle is just a sort of qualitative way of thinking about the same things. With Le Chatelier's principle, there's three primary stresses that we'll apply to the system. One is a change in concentration. So for example, we may add a reactant or a product, or we may remove a reactant or a product. If we add something, the reaction will proceed away from the substance that was added. So if we add a product, the reaction will go in the reverse direction, because going in the reverse direction uses up the product and helps to reestablish equilibrium. If we remove something, the reaction will proceed toward that substance because it's trying to make more of it. So, for example, if we remove one of the reactants, the reaction will proceed in the reverse direction because that will create more of that reactant. Volume and temperature are a little bit tricky. For volume, if we're talking about gases, we might think about a decrease in volume, which would increase the pressure of all of the gases, and then the reaction will proceed toward the side that has fewer moles of gas. And vice versa, if we increase the volume, it proceeds toward the side with the greater number of moles of gas. When we're talking about solutions, and that's what we'll be studying in this lab, we may change the volume by adding water, which is just diluting it. When we dilute it, it decreases the concentrations of all of the solutes. So the reaction will proceed toward the side with a greater number of moles of solutes. Temperature affects reactions differently depending on whether they're endothermic or exothermic. In an exothermic reaction, if it's heated up, it will go in the reverse direction, whereas in an endothermic reaction, if it's heated up, it goes in the forward direction. So heat is treated like a reactant for endothermic reactions and a product for exothermic reactions. That's a brief review of the concepts that you need to know for lab today, and now I'm going to talk about some of the calculations. The reason I'm going to spend a little bit more time on the calculations is because you're going to be asked to analyze some data from a similar experiment to the one that you're doing, but one where we were able to measure the absorbance of the product of the reaction. And so we have quantitative data as opposed to just qualitative data about which direction the reaction proceeds. So for the calculations, the first thing that you'll be asked to do is find initial concentrations of reactants. And this is simply a dilution calculation, M1V1 equals M2V2. For example, if you have 2 milliliters of 0.5 molar CuCl2, and then you dilute it to a total volume of 10 milliliters, you take your 2 times your 0.5 and you divide by 10, and you end up with 0.1 molar for your new concentration. So this is just because you're going to be mixing together reactants, and so you have to have the total volume of the mixture taken into consideration for the concentration. Because the experiment that we're talking about can measure the absorbance of the product, we can use Beer's law to find the concentration of the product. This is especially useful because it means that then we can figure out how much reacted and how much is left of our reactants, and then calculate the equilibrium constant. So as a reminder, Beer's law is absorbance equals epsilon Cl, where C is the concentration in molarity and L is the path length. And in all of the instances that you'll see in this class, it's always 1 centimeter. So if we have an example where the absorbance of the product is 0.75, then we would divide by the epsilon, which in this case we'll say is 50, and the path length, which is 1, and we come up with a concentration of 0.015 molar. All of these examples, by the way, you can go ahead and do them on your own to make sure that you get the right answers. Now, it turns out if we know the initial concentrations of reactants, which we just figured out doing our dilution calculation, and we know the equilibrium concentration of the product, which we just figured out using Beer's law, then we can calculate the equilibrium concentrations of everything else. We just use stoichiometry, and a rice table is a nice way to keep track of everything. So I'll do a quick example. In this case, we have a closed system. This is a gas phase reaction with hydrogen and iodine gases forming HI. We know the initial concentrations of H2 and I2, and we know the equilibrium concentration of HI. So this is the thing. We know because of the stoichiometry, when we start with all reactants, we're going to go towards products. So we'll lose some amount of the reactant, and that'll be, let's say, X. And because hydrogen and iodine are in a 1-to-1 ratio, we also lose X amount of I2. In this case, HI has this coefficient of 2. And because it has the coefficient of 2, we know we're going to get 2 times the amount of HI as each of the hydrogen and iodine that has reacted. So now we have a situation where we know that 2x is the same as 1.87 times 10 to the minus 3. That means we can solve for x. X is just 9.35 times 10 to the minus 4, half as much as our 2x. Given this information, we can fill that in for all the x's in our tables, and now we just take the amount we started with and then we subtract the amount that has reacted to get our equilibrium concentrations. Now the reason we're doing this is because in the end, our goal is to find the value of the equilibrium constant. That can tell us important information about the nature of the reactants in the products and whether the reaction will be spontaneous. So with our equilibrium concentrations, we're just going to plug them into the equilibrium expression. So I've written it out here. We plug in our values and we can calculate our K. In this case, it's 51. All of those calculations leading to calculating the equilibrium constant are the first part of what you'll do with the data from the Excel spreadsheet that we're sharing with you. And they're on the K calculations tab of that spreadsheet. So you can check your work there to make sure that you've done the calculations correctly for that reaction. The second thing we ask you to do is to think about the temperature dependence of K. Now in lab, you're going to see this based on just the color of the solution that you're looking at. But if we're able to get quantitative data, like we've just described, then we can actually calculate K at different temperatures. And the equation that we use to calculate K at different temperatures is this Hoff equation. The natural log of the equilibrium constant equals negative delta H over RT plus delta S over R. And this is in a sort of y equals mx plus b configuration here, where the slope is going to be negative delta H over R, and the intercept is going to be delta S over R. So depending on the properties of the reaction, we would expect it to have either a positive or negative slope. If it's an exothermic reaction and our delta H is negative, then when we look at our slope, which is negative delta H, we expect a positive slope. And if we have a positive change in entropy, then we expect our intercept will be positive. And if our change in entropy is negative, then our intercept will be negative. And we can actually calculate the values of delta H and delta S if we have data along this line plotted ln K versus 1 over T. We just use the slope to be negative delta H over R and the intercept to be delta S over R. In lab today, you're going to be looking at a reaction between this CuH2O6 2+ complex ion and this CuCl4 2- complex ion. Now, this is a sort of picture to illustrate that they have slightly different colors. This one is a light blue color, and then if you have a mixture, it turns out to be sort of turquoise looking. And if we have primarily this chloride complex ion, then we get a light green color. I'm pointing this out. This is a subtle color change, so you really have to look carefully at it. I recommend having a piece of white paper or something that you can hold it up to and having good lighting to make sure that you can see the difference. And of course, if you're colorblind, get some help from a friend. An interesting thing to notice here is that there are actually 6 molecules of water that are bound to this copper ion, and they make 6 coordinate covalent bonds. On the right side, where we have the copper and the chloride complex ion, we only have 4 chloride ions that are able to surround the copper because the chloride ions are larger. So you can't fit as many around the copper ion. And that means there's only 4 bonds. So that's an important thing to think about when you're predicting whether this reaction will be endothermic or exothermic, and also whether it will have a positive or a negative change in entropy. In lab, it's important that you follow all of the normal safety regulations, wearing long pants and closed-toed shoes, your goggles at all times, and gloves and an apron. The silver nitrate that you're going to use will stain your skin, so you should be especially careful with that. Also, copper chloride and silver nitrate are irritants, and copper chloride is corrosive. Silver nitrate can cause damage to aquatic life, so there are special instructions for how you should dispose of the silver nitrate solution, and make sure that you're following those in your procedure. Now, the reaction that you're going to be looking at from the data is actually a different reaction, and it's a complex ion formation reaction for this FeSCN2+ complex ion. Our iron is a yellow color, like this test tube on the right. SCN, or thiocyanate, is just colorless. FeSCN2+ is this deep blood red color. And then if you have sort of a mixture, it will be orange. So in your lab report, you're asked to think about how this reaction would be the same as or different than the reaction that you're looking at in lab based on the data that you're given in that spreadsheet. And also thinking about the molecular level, what's happening. In this reaction, of course, you're forming a bond between the iron ion and the SCN ion, which tends to make something more stable because you're forming a bond that should be releasing energy. That's the end of our pre-lab lecture. I hope you enjoy the lab and have a great day.